In section 2.8, we're going to finish up this section on polynomials. We're going to go back to other information that we've already learned how to do, such as finding zeros, and we learned about end behavior, and we're going to put it all together so that we can graph our polynomials. And key new vocabulary you're going to have here is local maximum and local minimum. Those are very similar to the concept of the vertex in a quadratic function, which only turns one time, but in higher polynomials, it may turn several times, and then the highest or lowest point for a section of the graph is called the lowest maximum if it's the highest point, and the lowest minimum or local minimum if it's a lower point. Problems that might be solved using the skills we're working on in this section are items like this, where we have a certain amount of cardboard and we want to maximize the volume of the box we're going to make from this. To make the cardboard, we're going to have to make cuts here and determine the depth. So just notice that if we are cutting in here, we're going to change this value of x, which has to come out of the overall size of our cardboard sheet. So what value of x, or what depth, do we create to maximize the volume of this box? And we're going to do that by graphing a polynomial and then finding a local maximum. But before we do that, we want to go back and make sure we remember that zeros, right? Zeros are x-intercepts. They're also called solutions. And we'll call them a value of k. If I know that a solution k, or 0k, exists for my polynomial, then x minus k is a factor. K is a solution, right? So we call it a zero, we call it a solution. And if k is a real number, then it is an x-intercept. If it's an imaginary number, then it's not an x-intercept. And our graph of f of the function passes through k0, meaning that's how we graph our x-intercepts. Okay, so these are all concepts that we talked about during the last two chapters. And let's just go through and take a look at what our k values are. So we want to look at what's going to happen with our polynomial, right? So I can find my solutions. I have a repeated solution of 2, right? So my solutions are 2, 2, and negative 1. I know that because my factors are x minus 2. They squared it, so that happened twice. And x plus 1. And when I set these each to be equal to 0, these are the solutions I'll get. So I know I have an x-intercept here and an x-intercept here. Okay, and I also know that this is squared. So when you have a repeated solution, it does something special on the graph. A repeated real solution actually is a local maximum or a local minimum. If I were to multiply this out, I'm not going to, but if I were to multiply this out, you can see my leading coefficient would, or my leading term would be x times x times x. That would be x cubed. So I'll have 1x cubed. So I have a positive leading coefficient. That means my right end goes up. I have an odd degree, which means my ends do different things. So I know generically that my graph comes in this direction, comes back down. Now, I happen to know that repeated solutions are local maximums or minimums, so I know it's going to turn around here. If I want to find more data, how much more data do I need? I know that from here it approaches positive infinity or negative infinity. I know that in this area it's going to touch the graph and it's going to go out there. So what I really need to know is, what does it do here? So I'm going to look, if I were using a graphing calculator, I would go ahead and multiply this out, find the polynomial, and I'd plug it into my graphing calculator, and I'd use the trace function to find this local maximum. This is a local minimum, right? So I know that 2, 0 is a local minimum. And whenever you have a squared binomial, it's going to turn right on the x-axis. So that's my local minimum. I want to find, sorry, I did a terrible job underlining that. I want to find a local maximum. And if you're going to be working without a graphing calculator, it would be sufficient for you to find a point halfway between these two solutions. So between 2 and negative 1, that's going to be 1/2. Okay, so if I plug 1/2 into my polynomial, I'll have 1/2 minus 2, the quantity squared, times 1/2 plus 1. So this is 3/2. 1/2 minus 2 is negative 3/2 squared. So this becomes 9/4 times 3/2. That's 27/8. 27/8 is about 3.5, right? Almost 3.5. 28 would be 3.5. So 1, 2, 3.5, right about here. Right? That's my graph. And I would just use the fraction. 27/8 is my local maximum. Okay, if you were using a calculator, you could find something that was a little more precise. Later in the lecture, I'll use a graphing calculator and I'll be more precise when I find those. But if you're working on a test or a quiz and you don't have a graphing calculator, that doesn't mean just stop and throw up your hands and don't do the work. Go ahead and estimate what your local maximum is. Okay, if we have another problem like this, you can see I've got 1, 2, 3, 4. I have negative 1, negative 1, 1, and 3 as my solutions. So negative 1 is a solution. I have 1 as a solution. 2, 3 is a solution. I know if I multiply the first terms, again, remember I have two binomials here. And if I just take all those first terms in all my binomials and multiply them together, I'll get 1, 2, 3, 4. I'll get 1x to the 4th. Leading coefficient is positive, so I know my right end goes up. It is an even polynomial, so I know that the other end goes up, and I know that this point here is a repeated solution, so I know that this happens. And I know it's going to come down here, and I know it's going to go up through there. Right? That all makes sense. But what I need to find are these local minimums and maximums. Okay, so I know that over here I don't have to worry about it, and over here I don't have to worry about it. I want to plug in a couple of different points. I'm going to plug in 0, and I'm going to plug in 2. Right? So I'll have 0 plus 1 squared, 0 minus 1, 0 minus 3. So this is 1 squared, which is 1, times negative 1, times negative 3. So this will be equal to 6. 1, 2, 3, 4, 5, 6. So I know that I turn here, I go all the way up to 6, I turn back around, I come down here, and when I plug 2 into this, I'll have 2 plus 1 squared, 2 minus 1, 2 minus 3. 2 plus 1 is 3, 3 squared is 9. 2 minus 1 is 1, 2 minus 3 is negative 1, so I have negative 9. That's all the way down here, so this is my local minimum. Okay, so if I want to smooth this out a little more, these ends are, whoa, that was a big eraser. These ends are probably a little wacky. Right? We're going to go back up and out like that. Going to come through here, go through there. And this is pretty much what my graph is going to look like. Okay, again, I was estimating my local maximum and local minimum. Mostly that's because I want you to understand that if you don't have a calculator, there are ways to go about this. Remembering again, when I have a binomial, the turn happens right on the x-axis like that. And then I'm estimating local maximum, local minimum. 2, negative 9 is my minimum, and 0, 6 is my local maximum. Okay, so go ahead and practice that. Do problems 7 and 8, and then come on back. Right, so when we talk about turning points, it helps you to know how many turning points they have. You could see, though, that by knowing how many zeros I had and working with end behavior, I was able to do that pretty well. But that works with real solutions. It's very difficult to do with with imaginary solutions because I don't have x-intercepts for imaginary solutions. So remember, the y-coordinate of the turning point is a local maximum. The y-coordinate of a lower turning point is a local minimum. That's what we just did. And knowing how many there are, the graph of every polynomial function of degree n has at most, that doesn't mean that's how many it has at most n minus 1 turning points. So one less turn than the degree. And if you think about polynomials you've worked with, a linear function doesn't turn. It's a first degree. N minus 1, 1 minus 1 is 0, 0 turns. That makes sense. You know, a quadratic function is second degree. It has 1 turn. 2 minus 1 is 1 turn. So this matches the experience you have graphing. And now we're just putting it into a rule. Right? So if a polynomial function has n distinct real zeros, again, the key element here is real zeros, then its graph has exactly n minus 1 turning points. So when you have imaginary solutions, sometimes they have the effect of eliminating turning points. Okay, and that n distinct real zeros, that means no repeated solutions, because repeated solutions can also eliminate turns. Okay, so that's, you have this rule, this concept here, but it does have its limitations, and it's important you understand the limitations and what causes them. So if we want to find turning points with these guys, how many would I have? I have a third degree polynomial. I'm expecting to find 2 turning points, right? And I went ahead and I put this guy into, again, a graphing function. Right, so here's the graph of this particular equation. I have 2x cubed plus 8x squared minus 3. You could use your TI. I instead use this tool. You can see I have a turning point here of about minus 2.67, and the maximum here is 15.963, so basically 16. And my minimum is at 0, negative 3. So negative 3 is my minimum, my local minimum, and 16 is my local maximum. And I did the same for the other example. Let me go ahead and write that down. So I have 0, negative 3, and I had essentially, let's go ahead and go back. We had negative 3, 16 for our local maximum. Right? So maximum, minimum. So when I take a look at this polynomial and I put it into the same graphing function, see, this is what it looks like when I have imaginary solutions. So you can see I have 1, 2, 3 solutions. You'll always have one less turn than the number of solutions you have. But this little wrinkle here, this little sort of anomaly in the pattern, this is caused by imaginary solutions. So you can see that for local minimums, what I've got is, or my local maximum is negative 1.63, 10.47, and my minimum is 1.46, negative 1.68. Okay, so really difficult to find these if you were working as an individual without a graphing calculator or without a tool. Okay, so that's how it goes, but what's important for you to understand is that this is what it looks like when I have imaginary solutions, and you can see that imaginary solutions took away 2 turns because it also took away 2 real solutions. So normally with a 5th degree polynomial, I would expect 5 solutions. 5 real solutions would have 4 turns. Because I have 3 real solutions and 2 imaginary solutions, then I only have 2 turns instead of the 4 I expected. So if you go back also to think about what we did in section 2.7, how Descartes' rule about being able to find the different types of solutions you're going to have can help you if you're working through graphing. So if you know they're imaginary solutions, then you can predict that some of these changes might happen. Okay, if we want to continue on and practice, go ahead and do problems 27 and 28. If you don't have a a graphing tool. You'll notice I use this Desmos graphing calculator. It's free, it's online, it's pretty easy, and it works really well. So you can go ahead and use that to help you out. And then come on back, we'll finish up the lecture. So in working with this particular problem, we want to write a model that's going to graph the different volumes we could have. So I know that my cardboard is 16 inches, and I'm going to create this height, x. I don't know what height to make it. But I know then that this side here will be 16 minus 2x. Because I'm going to take the total amount of 16, I'm going to take x out of it twice. And this other dimension, my width, would be 20 minus 2x. And my height would be x. So this is the volume. I have length times width times height. And if I multiply this all out, I'll get 4x squared. I'm also going to put it in the right order. Right? I'll get 4x squared minus, I'm sorry, not squared, 4x cubed minus 72x squared plus 320x, and that's equal to my volume. Now I could go through and I could find solutions for all this, but I really don't want solutions. My solutions are 8 and 10. I know that now because 8, 10, and 0 could all be solutions. But remember, that's not really what we want, right? That's what makes the volume equal 0. We don't want the volume to equal 0. We want to find the maximum. So what we're looking for is a local maximum. So I'm going to go back to my graphing site, and I've got this one graphed here. If you want to take a look at what the whole graph looks like, it's very vertical, right? But if I zoom in, you can see some of the details that I talked about. First off, I told you my solutions are 0. My solutions are 0, 8, and 10. And here they are down here, but that's not what I'm looking for. I'm looking for maximum volume. So if I come all the way up here to my local maximum, you see it's 2.94, or essentially 3, and 420.11. So if we take that 3 and we go back to our function and we plug 3 back in, I'll have 16 minus 2 times 3, which would be minus 6. 20 minus 6 times 3 is equal to, times 3 would be equal to my volume. 16 minus 6 is 10. 14, 3. So this is 42 times 10, so my volume would be 420. And you can see by being slightly less than 3, I got infinitesimally more volume, 0.11 more from the graph. But this is how we went about solving.